For a gas turbine, a jet engine, what we can do is we have the compressor, the combustor, and the turbine, and those components we've analyzed for the stationary power plants, the Brayton type cycle stationary power plants. But we add, because you may need a diffuser to slow down the incoming air so that it's not so fast through the compressor combustor turbine. So you add that component, the diffuser, and you also add the component of the nozzle, right? And notice that what the turbine produces drives back to the compressor. Maybe I'll show the shaft not interfering here. And so there is no net power developed by this that goes externally. The power developed by the turbine is the power consumed by the compressor. And one of the keys is this nozzle, because the nozzle accelerates the flow such that the kinetic energy at B is high. You want it high. Higher the better. Because it's velocity exit, or VB squared divided by 2. Isn't that the kinetic energy? So you want that as high as possible, which is great for propulsion. So why did they use the letter A for a state and the letter B for a state when most of the book uses numbers 1, 2, 3 for states, right? Well, because I don't think they wanted to go back and use letter 0 or number 0 and number 5. That would have been just as fine if they would have. But trying to be consistent with this textbook, they did switch and use a letter for the state, A coming in and B for the exit. So we have to be able to analyze the diffuser. So if we do an energy balance around that diffuser, what do we get? Is there any work? Is there any heat? It's running at steady state. And so what comes in, the enthalpy coming in plus the kinetic energy coming in, goes to the kinetic energy at 1, and often the kinetic energy, the speed is negligible other than at state A and B. The kinetic energy at 1 is negligible, at 2 it's negligible, at 3 it's negligible, and at 4 it's negligible. That's our common assumption. So what we can do is we see, oh, in this diffuser, assuming isentropic process, there's no irreversibilities in the diffuser. You can specify it, but it just is an extra step. This is often the case, that the diffuser is isentropic. You'll often have a isentropic efficiency for the compressor, isentropic efficiency for the turbine. Really, there's no isentropic efficiency for the combustor. There's nothing like that. And then the diffuser and the nozzle will be isentropic, no irreversibilities. That's our common assumption. So what happens, talk to me about the pressure at A and the pressure at 1. Talk to me about the temperature at A and the temperature at 1. We see from the energy balance what happens. So if I have some non-zero inlet kinetic energy, it goes to increase the enthalpy at state 1, true? So what about the temperature at A versus temperature at 1? Which one's greater, temperature A or temperature 1? Or the same? Are they the same? It's going to be like this, true? T1 is greater? How can you see it from this equation? Maybe you write it like this. You say that the energy equation in terms of constant specific heats, which are pretty good, but it really illuminates the behavior with constant specific heats. You see the relationship easier. You see that 1/2 VA squared is equal to C sub P T1 minus TA. So if I have some non-zero velocity coming in, speed coming in, then T1 will be greater than TA. Yes, sir. Okay, now how about pressure? Pressure. How do I get the relationship between pressure? Did the pressure go up? Did the pressure stay the same? Did the pressure go down? Think about it for a minute. What would you use to guide the analysis? Especially, is there an analytic expression? Is there an analytic expression like this? That T2 divided by T1 is equal to P2 divided by P1 to the power K minus 1 over K. What is that? That's a relationship for an isentropic process. S is equal to constant for an ideal gas. Okay. So can I switch it like in, well, put it over here, K over K minus 1 and get it off of there? And then, so now that maybe helps a little bit. What about T2 compared to T1? In this case, I know that I'm switching here. You want me to update the subscripts? So if I update the subscripts, it'd be the pressure at 1 is equal to the pressure, or divided by the pressure at A, is equal to the temperature at 1 divided by the temperature at A to the K over K minus 1. So it's equal to something that's greater than 1. T1 is greater than TA, so this is something like, I don't know, I'm just going to throw a number in there, 1.1, some number. I'm just making that up. It's greater than 1 raised to an exponent, this power, that is also positive. Now, it's 1.4 divided by 0.4, whatever that ratio is. Okay? Right? It's raised to the power 1.4 divided by 0.4. So looking at this, what about P1 and PA? Same? No, not the same. It was interesting. We thought it might be the same. We guessed that it might be the same. But P1 is greater. It actually built up the pressure. Diffusers are really interesting devices. It's where you finally have, it's almost an oxymoron, flow into a region of increasing pressure. The flow went from low pressure at PA to higher pressure at P1. And in the process, it slowed down. It slowed down. Bernoulli's equation will explain the same thing, true? Because if Bernoulli's equation assumes it's reversible or it's isentropic, it's frictionless flow. So the pressure will go up when the kinetic energy goes down. And that is explained also by Bernoulli's equation. But there you go. Now we have done the hard job of analyzing this diffuser, true? When you march across, the compressor's not much different than what we've done. The combustor's not. Usually the T3 is specified. Oh, it's 1500 Kelvin. It's some maximum temperature. It's usually specified. Also, the pressure ratio across the compressor is usually specified. P2 over P1 is often given, the pressure ratio for the compressor. Okay? But now we come to the turbine. And I say, if this pressure ratio P1 to P2 is given, and let's say it was given to be 10 for this problem. I'm looking at this turbine, and this is a tough question. And I know some students, when I asked the previous question, is it greater, is it equal to, is it less? And then some brave student said, I think it's equal to. And then I just went on to explain that no, it's not. That they're not going to answer another question for a while in my class. They're going to be so gun shy, right? They're like, I don't trust Monteufel. I don't like the way he asks questions. Because when he asks questions, then I answer him, and then he shows me that I was wrong. That's not the point of my asking questions, but I know that's happened. So this is the trick question now. Is the pressure at 4 divided by the pressure at 3? If the compressor pressure ratio is 10, is it the 1 over 10? You're tempted to say yes. You're tempted to say yes, aren't you? Because that's the problems you've been solving so far. But just like there was an increase in pressure through the diffuser, you have to know a little bit about the nozzle. Do nozzles work well when pressure at 4 is equal to the pressure at B? Or would the nozzle work better if the pressure at 4 is greater than the pressure at B? It would work better at kicking out that gas at a very high speed, at a very high speed. So I'm going to tell you that this is wrong, and we'll come back and fix it in a minute. But we'll explain why it's wrong by understanding the nozzle. Understanding the nozzle. So we already know we really want the kinetic energy at B to be very high. We want the speed of B to be very high. Do I have a similar equation like the energy equation that I applied for the diffuser? Can I write an energy equation for the nozzle? Sure. How would it look? Would it look like this, the energy equation for the nozzle? Would it look like the enthalpy at 4 plus the kinetic energy at 4? Professor, I thought we said that was negligible. You're right, it is negligible. Let's say that's equal to 0. The kinetic energy at 4 is equal to the enthalpy at B plus the kinetic energy at B. Yeah, that looks pretty good. Thumbs up. You like that? Yeah. Good. Now what we do is we want the kinetic energy at B to be high. So we'll write this equation. The kinetic energy at B is equal to, assuming constant specific heats, C sub P T4 minus TB. Does that equation make sense? Can you see how you got that equation? So if I want a high kinetic energy at B, I want either a high temperature at 4 or a low temperature at B, don't I? One of those. Give me a large contrast, a large temperature difference through that. True? True? Can I apply this type of equation right here, which is isentropic process for an ideal gas, how T's and P's are related? Can I apply that for the nozzle? And now I'll bring that equation into play for my nozzle, and we'll say that the temperature at 4 divided by the, let's try this one. Temperature at B divided by the temperature at 4 is equal to the pressure at B divided by the pressure at 4 raised to the K minus 1 over K. I'm going to pause and I'm going to let you look at that for a minute. And I want you to buy in and say, yes, I agree, that equation looks correct. Does it look correct? Give me a thumbs up when you. If I look at this equation and I want TB to be very different than T4, what about that pressure ratio, PB and P4? If PB is equal to P4, guess what? The difference in temperature is, I don't have a very good diffuser, do I? No. Or a nozzle, I'm sorry, not a very good nozzle. So what happens is you really want this P4 to be as high as possible. And you want PB, the exit pressure, to be as low as possible. Well, guess what the exit pressure truly is? You can't really control that. It's the ambient atmospheric pressure wherever the engine is operating. If it's operating at 30,000 feet, that's different than at ground level. But it's whatever the ambient pressure is. Is it the same as PA? Is PB equal to PA? It is. It is the same. It is the same. And how many people have already taken fluids? You're in it right now. And you're going to learn about streamlines and pressure across streamlines, okay? Doing it right now. And that helped guide you answer that question, huh? Because this is one of these, another oxymoron, let me try and address it, is you have this jet engine and it's maybe like this, and the gases are just shooting out, like that. And the question is what is the pressure here compared to the pressure right in the middle of those shooting out gases, just coming out of that? And intuitively, you take your hand, conceptually, you don't run to it, real jet engine, and you put it up there and you say, hey, how's the pressure here? And if you try to put your hand right here, right, your hand is going to get blown away because basically your hand it's disturbing the flow. It's trying to bring to rest that high velocity gas, which is going to put a high pressure on one side of your hand and push it out of the way, true? So don't conceptually put your hand up there to sense, what's the pressure coming out the back of this jet engine? That may be why some people think it's high pressure right in here. But you use, what did you just learn from fluids? Okay, but to go across streamlines, Bernoulli's is to stay on a streamline. And then if you have curved streamlines, I have curved streamlines, and I want to know what's the difference between this pressure and that pressure going where you have this instantaneous radius curvature going out, right? There's whose equations? Newton's. I know he did a lot. Good guess. But somebody else did something in science and engineering other than Newton. Maxwell. Good try. Good try. He did a lot. Who did it? True? Does that help? Do the keyword search and you may find it. But he explains it in this relationship. I think they attribute his name to it. I may be wrong, okay? Sorry if I'm wrong. But basically, what's the radius of curvature for straight lines coming out? Infinity. And when you have infinity for that radius, then the pressure is no different going all the way across. It's the same pressure. And so, boom. So the pressure coming out, the pressure coming out at B is equal to the pressure going in at A. It's the local ambient pressure. There's a lot behind that, but it's what you have to know. So, okay, so I really want a high pressure at 4 so that the temperature at B is a lot lower than the temperature at 4. And don't worry about sending out cold gases. Don't worry. It's so hot you don't want to put your hand around there. It'll be hot, right? You're not making a refrigeration system and expelling cold gases. These are really hot gases still coming out of that jet engine. And so you want this pressure at 4 to be as high as possible. Well, that means that this is not true then. How do you know then how far to bring down the pressure at 4? The pressure at 3 is definitely higher than the pressure at 4, but how far down do you go?
Well, you know the pressures from 2 to 1 or 1 to 2 is going to be 10, right?
Right.
You know that the compressor is going to have some enthalpy change, while the turbine is going to have the same enthalpy change if they both are isentropic, right?
Right.
So then you can figure out the pressure off the cables.
Okay. But basically, one fact that you have to remember, what is the one, I think the nugget, the little insight, to grab a hold and remember, this is what makes it work. What is it that you have to remember, the relationship of the turbine? It has to run the compressor, and that's all it has to do. That's all. If you remember that, it'll guide you to the right solution. So what you do is you come back and you say, well, the work out of the turbine, assuming the same kilograms through it, so I'm using a lowercase w for the work out of the turbine, is exactly the work required to run the compressor. Now, if you have efficiencies, there's a few steps between getting the isentropic work and the actual work for the compressor, and there's the same steps or like steps for the isentropic work of the turbine and the actual work of the turbine, but it's still very doable. These have to match. The actual work needed to run the compressor has to equal exactly the same actual work produced by the turbine. True? And once you have that, it all falls into play, because then it's like, I don't know what P4 is. I know this. And now, if you just think about it, if P4 is equal to P3, I don't get any work out of the turbine. So I just bring down P4 conceptually in my mind low enough so I produce enough work out of the turbine to run the compressor, and then I have as high a pressure left to drive the flow through the nozzle. You can put this on a diagram, a temperature entropy diagram, and we do have a bunch of lines of constant pressure. Here's one, which is the pressure at A, and it goes all like that. Okay, but we're going to start at state 1 here, and start at state A, and we go through the diffuser. The temperature goes up. The entropy S, it doesn't go up. It's isentropic, so it's a straight line up, and it goes up a little bit to 1. And the pressure at 1 is not the same as the pressure at A. It's a higher pressure. We just talked about that, true? Then you go through the compressor with the pressure ratio going from 1 to 2, and if it's isentropic, it's straight up to 2. If there are some irreversibilities, you still achieve the same pressure ratio, but it'll kick over a little bit, and it'll actually come up from 2S to 2 actual. Does that little discussion make sense? So you think about going straight up and straight up, but if you have the efficiency of the compressor, you have to modify 2S and 2. But 2S and 2 have the same pressure. And it's P2 is dictated by the pressure ratio times P1. Now, you go through the combustor. Well, this is where it gets spanking hot, and it goes way out here, and I'm sorry, I think I made my diagram almost. Let me try and fix this red line. Come like this. Maybe I'll be able to see it. So I don't have a lot of room, but isn't this T3? Now you go to a lower pressure at P4, and you probably want to keep P4 as high as possible. So this is the line P4. This was the line P1. This is the line PA, which is PB. And this is a line of P2 is equal to P3. So we have these pressure lines in there. Okay, now we drop down and we go to 4S. But if it's irreversible, you get over to 4 actual. Then you drop from 4 actual straight down again to B. So you really would like this difference, this drop, to be as large as possible so that you can have a high kinetic energy at B.